Let's discuss resonance. In the nitrite ion, two oxygen atoms and one nitrogen atom undergo bonding in order to stabilize themselves and to complete their octet. The valence electrons of each bonding atom decide how many bonds an atom can make. Some of the electrons in each atom are unpaired and some are paired. The unpaired electrons take part in bonding and make bonding electron pairs, while the non-bonding electron pairs remain intact. How many electrons take part in bonding and how many remain non-bonding? We can find their number by using the concept of formal charges. So let's calculate the valence electrons of nitrite ion. 5 electrons are in the valence shell of nitrogen. For two oxygen atoms, 2 times 6 electrons are present and 1 for negative charge. So the valence electrons in nitrite ion are 18. These 18 electrons are distributed around 2 oxygen atoms and 1 nitrogen atom to complete their octet. Let's calculate the total number of electrons which are required to complete the octet of each atom. Multiply the number of atoms with 8. So in this case, 24 electrons will make the octet of each atom complete. But these are greater than the available valence electrons. So we can say some of the electrons are being shared between the atoms. How many electrons are shared? Let's find the difference between s and valence electrons, which gives us that 6 electrons are being shared between 2 oxygen and 1 nitrogen atom. During bonding, the atoms are spaced in such a way so as to minimize the repulsions and to lower the energy of the system. This gives rise to the particular shape and geometry of the molecule. For the nitrite ion, the atoms are spaced in angular form. The geometry of nitrite ion is angular. These 3 atoms are in plane. Fill up the 6 bonding electrons. 4 out of 6 bonding electrons will make 2 sigma bonds, while the remaining 2 bonding electrons will make 1 pi bond between nitrogen and oxygen. Now, 6 out of 18 valence electrons are filled. Remaining electrons will be non-bonding, but the electrons would be arranged around each atom so as to complete the octet. In the case of nitrogen, it is surrounded by 3 bond pairs, which means 6 electrons. It is 2 electrons away from octet. So 2 electrons in the form of one lone pair is surrounding nitrogen. This oxygen is surrounded by 2 bond pair, which means it is surrounded by 4 electrons. It is 4 electrons away from octet. So it has 2 lone pairs. While this oxygen is surrounded by 1 bond pair, which means 2 electrons, and it needs 6 electrons to complete its octet. So 2 bond pairs and 1 negative charge is present on it. There is a possibility that this negative charge shifts between oxygen and nitrogen, and this pi bond breaks off and negative charge comes on oxygen. This results in a structure of this. Both these structures are interconvertible, and both are the canonical forms of nitrite ion. This double-headed arrow is used to represent the 2 canonical forms, and this phenomena of shifting of the electron and breaking up of pi bond is called resonance. The actual structure of nitrite ion is the hybrid of both canonical forms. The dotted line is showing the delocalized chemical bonding, and this whole structure gets a negative charge on it. From this, we can conclude that resonance is a delocalized chemical bonding phenomena involving p-orbital, and there must be a pi bond or lone pair of electrons at conjugate positions. For resonance, there are certain rules, which we can conclude from the example of nitrite ion, that the canonical forms are not the actual structures, and the actual structure is a hybrid of its canonical forms. All the structures must be bonafide Lewis structures. All the bonds must be justified. In canonical forms, we are allowed to move the electrons only. There must be the same number of unpaired electrons in each canonical form. Atoms involved in resonance must be in plane. All the canonical forms don't contribute equally. We have discussed in this example that the resonance structures are not the actual structures and the actual molecule is a hybrid of canonical forms. So let's discuss the third rule of resonance, that all the structures must be bona fide Lewis structures. Let's consider the example of acetate ion. This negative charge shifts between carbon and oxygen and this pi bond breaks off, resulting this structure. Both these structures are canonical forms. If this negative charge shifts between carbon and oxygen and this pi bond does not break, giving 5 bonds of carbon, this would not be the canonical form because here the bonding of carbon is not justified, and it is one of the rules that all the bond must be justified. All the structures must be bona fide Lewis structures. So structure number 3 is not the canonical form. And acetate ion has 2 resonating structures. Discuss another example. Acetic acid. The lone pair on oxygen shifts between carbon and oxygen and this pi bond breaks off, giving this structure. Now this negative charge can shift between carbon and oxygen and this pi bond breaks off, but instead of going to the oxygen, it shifts between oxygen and hydrogen, giving 2 bonds between oxygen and hydrogen. This canonical form is not correct because here hydrogen is making 2 bonds. So 1, 2 are the canonical forms of acetic acid structure, while the structure 3 is not correct. Consider another example of nitromethane. The negative charge on one of the oxygen shifts between nitrogen and oxygen and double bond breaks off, giving this structure. Now if negative charge shifts between nitrogen and oxygen, giving 5 bonds to the nitrogen, this structure would not be justified and it is against the rules of resonance. So structure 1 and 2 are the canonical forms while structure 3 is not correct. So this is the third rule of resonance, that all the structures must be bona fide Lewis structures. All the bonds must be justified. Let's discuss another rule. In canonical forms, we are allowed to move the electrons only. Consider this example. Here the positive charge is on the third carbon and double bond is between first and second carbon. This double bond shifts between second and third carbon and this positive charge comes on the first carbon. But if double bond shifts between first and second carbon and hydrogen from fourth carbon shifts on the third carbon and positive charge comes on the fourth carbon, this structure is not justified according to resonance rules because here the hydrogen is shifted. So structure 3 is not correct. In this example, hydrogen is shifted to this oxygen and the pi bond shifts between 2 carbons. These are not the resonating structures but are the tautomeric forms. So structure 1 and 2 are not the canonical forms but the tautomeric form because here the atom shifts, not the electrons. There must be the same number of unpaired electrons in each canonical form. Consider this example. Here, this carbon contains negative charge and this carbon has positive charge. There is a possibility that negative charge shifts between these 2 carbons and pi bond breaks off and shifts between these 2 carbons, like this one. But if we break the bond homolytically, like this, half bond shifts on this carbon and half bond shifts between these 2 carbons. 1 electron goes here and 1 electron goes on this carbon, resulting this structure. This is not correct resonating structure. Atoms involved in resonance must lie in plane. This is cyclooctatetraene molecule. This is a tub-shaped molecule in which conjugated double bonds are present, but these are not in plane. So there is no resonance in cyclooctatetraene. All the canonical forms do not contribute equally. Here are certain rules for major and minor contribution of canonical forms. Consider this example of aniline. Nitrogen is having one lone pair. This structure is another canonical form of aniline, where the benzene is having bond shifted to the other positions. There is a possibility that these lone pairs are shifted between nitrogen and benzene ring, and these pi bonds are breaks off. Negative charge comes on this carbon. Now this negative charge can be shifted between these two carbons and this pi bond can break off. Now this is another resonance structure. But among these structures, these two structures will contribute majorly and will have the major contribution, while these three structures have minor contribution. According to the rules of resonance, the structures with more covalent bond are generally more stable, and the structure without charge separation are more stable. The structure which is stable have major contribution. Secondly, the greater charge separation, less is the stability. The structure which has greater charge separation would be less stable. When this pi bond shifts between these two carbons and positive charge comes on this carbon, negative and positive charge are separated. So this structure, according to the rules of resonance, is less stable and have the less contribution. Structure with like charges on adjacent atoms are highly unstable. Consider this example. One of the nitrogen is negatively charged and the other is positively charged. Its another canonical form is this one, where this negative charge shifts between these two nitrogens and this double bond breaks off and nitrogen gets negative charge. But this is another canonical form, where these two nitrogens are bonded with a triple bond and both get positive charge. This structure is less important according to the rules of resonance, because here like charges are on the adjacent atom. So these two structures will have greater importance and the structure 3 will be unimportant. The structure with negative charge on less electronegative atom are unimportant. Consider this example where the green color arrows are showing this structure, where double bond shifts between these two carbons and this triple bond breaks off and the nitrogen gets negative charge. Here nitrogen gets negative charge and carbon gets positive charge. Now this structure, where this triple bond breaks off and shifts between these two carbons and the double bond breaks off and carbon gets negative charge. Now carbon gets negative charge and nitrogen gets positive charge, while nitrogen is more electronegative than carbon. So this structure is less important and this structure is more important, because according to the rules of resonance, the negative charge on less electronegative atom makes the structure unimportant. So these two structures are important and the third structure is unimportant. Equivalent structures make equal contribution. Consider the benzene ring structures, where the Kekule structures have bond lengths and bond angles identical, while in the divorce structure, one of the bond length is greater than the others. So the structures which are equivalent make the equal contribution. These two structures make 40% contribution and these three make 7% contribution. But Kekule structure are more important while the divorce structure are less important, because resonance hybrid is more closely resembled to the Kekule structure. So we can conclude that the structures in which bond angles and bond lengths resemble closely to that of resonance hybrid are more stable. The greater the number of principal contributing structures, greater will be the stability of the molecule, and the molecule will be more stable if its canonical forms have equal energy. Consider phenol, which ionizes into the phenoxide ion. This phenoxide ion has resonating structures, which makes the phenol acidic. Because phenoxide ion is involved in resonance, the negative charge on the phenoxide ion is not available for attack, making it less reactive and more stable. So the structures which have greater number of principal contributing structures are usually less reactive and more stable. This is the reason that phenol is acidic in nature and its acidic nature is greater than the alcohols. So this was all about the rules of resonance. Thank you.